They may not be. One of them may be 0, one of them may be 2. So you have to go through this procedure to figure out what the coefficients are before you can solve for K. All right. So, you know, whoops, my bad. So in the end, you know, what we're really after then, if you're a chemical engineer, if you're trying to do this, how do I manipulate the concentrations to get the rate I want? You know, so if I want to make so much product, I need to make, you know, 500 pounds a day. Well, if I want to make that many moles coming off the back end, how many moles do I have to put in on the front end for the rate equation in order to be able to get that amount per day? So, you know, it really is important, and the whole point of all this is how do we get the reaction rate, you know, based on what the reaction concentration is. So, you know, the process we use, and this just summarizes what we just did. We find the exponents in the rate law. You have to have some experimental data, which I would give you. You know, if you look then at the changes in the individual reaction concentrations, you know, how does that depend on each one? So, you know, if you think about it a little bit, if we go back to our previous one, if I want to, whoops, wrong way, my bad. If I want to make this reaction speed up, you know, what's the best way to make that happen? I'd want to increase the concentration of B, right? Because, you know, I get a doubling or a 4x increase in the reaction rate for every time I double the concentration. So if I understand what this reaction is, I understand this rate law, it helps me figure out what's the best way to speed it up. In this case, you know, if I raise the concentration of B, it has a much bigger effect than if I raise the concentration of A. So, you know, designing a reaction, you know, that you want to try to maximize the rate of formation, you know, even though in the end, you know, when I get done, I still have to put in 1 mole of A for every mole of B. If I'm, you know, so if the product I want, you know, my job depends on making more of C every day. You know, it's still going to take one of these and one of these to make one of these. But I can make the reaction go a whole lot faster if I have more of this in there than if I have more of that in there. So, you know, by being able to look at this, you would be able to optimize your process to get the most product out the back end. I still got to put as much in, but just by doubling the concentration, I'm going to double the rate. Okay? So there are some really practical uses for understanding how kinetics and rates work. Okay, yeah, and then this is, you know, the order is always defined in terms of reactant concentrations, not products. So that's just sort of by definition and by convention, that's how we do it. Okay, so, you know, some other ways that we'll just go through it, and I know it seems like I'm just beating on this and harping on this, but there will be problems like this, and we will forget, and we will use the coefficients that are on the equation rather than the ones that we solved for, I'm sure. So, in this particular case, let's do this example. So we have S2O8, 3I3 going to SO4, 2 minus, and I3 minus. So this is the data that you would get. And again, you know, on a quiz or on a test, this is exactly what it's going to, you know, I'll give you a table of data like this. You know, concentrations, rates. So in this particular case, you know, what would be the first thing, again, if I said, okay, here's a reaction, here's some data, calculate K. What would be the first thing that we need to do? We need to find the exponent. So if you just look at this data, so let's find the exponent for X, for S2O8. So which reactions would we use? 2 and 3, right? Because we want to find one where I is constant. So, whoops, I did it backwards. Yeah, thought I remembered that. So we'll do this, then we'll go back. So we'll do 2 and 3. So if we do 2 and 3, okay, I is constant, so it's going to be 0.16 over 0.08 is 2, 2.2 over 1.1, 2. So first order, so X equals 1. All right, let's go back now. I did it backwards. On this one, so if we want to find out what the Y coefficient is for I minus, pick ones that are the same. So these guys are the same, they cancel out. 0.3 over 0.17, so 2. Rate goes by 2, it doubles. So in this case, it must also be first order in I. So in this particular case, you know, we might have had dumb luck and X and Y are both 1, right? So when we get to that, it is first order in S2O8, 2 minus, first order in I minus. Now that I have that, how would I get K? Just plug them in, right? So I can pick any of the equations. At this point, it doesn't matter which one I pick. I pick any of them. You know, I have a rate, I have this concentration, I have that concentration. If I calculate it, I should come up with, you know, 2.2 over 10 minus 40 divided by the 2 concentrations. Main thing again is, you know, just check the units. In the units, since it's second order overall, must be molarity to the minus 1 times second to the minus 1. And, you know, you don't have to remember that. All you have to do is look at the equation, right? this molarity cancels with that molarity. You know, we've got seconds to the -1, moles on the bottom comes up, moles to the -1. So, yeah, don't try to memorize what the units on K have to be. Just look at the expression, you can figure it out. So, you know, there's really, the entire semester, there's nothing you should have to memorize. So, but again, that would be exactly the kind of problem we'll have. You know, what's K for this reaction? You guys go through it and figure it all out, and you're good to go. Okay, good. So, you know, the next part, I got 2 more minutes. So, you know, once we get this, you know, the other useful part of this is then, you know, how does the concentration change as a function of time? So, you know, I figured this out. You know, now, depending on whether it's first order, second order, I should be able to tell you if I have a certain amount of a reactant at time 0, how much will I have 20 minutes later or 40 minutes later? You know, at any given time, I should be able to tell you how much is going to be left. And again, we use this rate law in order to be able to do this. The rate is just equal to a rate constant times the concentration raised to the appropriate power. So, you know, this will be, and we're going to use radioactivity as an example probably, but this will be one of the more useful things that comes out of this whole exercise, is that if I know the rate constant and I know the concentration at any one time, I can always predict what the concentration is going to be at a later time, given that the temperature stays the same. So, you know, the thing that we're going to have to remember for this is that depending on how we solve as a function of time depends on whether or not it's a first order, second order, or third order reaction. We're only going to do first and second order. We're going to do first order first, but when we're going to go through, you know, to do this, it's going to be important that, you know, 1, we understand that it's a first order reaction, and 2, that we use the appropriate equations, and we'll show you the equations how to do it. But, you know, so again, I might, if we step back a little bit and say, okay, gosh, you know, you have this much of the material at the beginning, I give you all of these, you know, the data, you know, and I say, okay, how much of A is going to be left 2 hours from now? First thing you're going to have to do, you have to figure out what the order of the reactions are. Then you got to figure out K. Once I get K, then I can figure out how far the time is. But just because the only question is how much is going to be left, you can't just jump right in. So, you know, you have to understand that you have to go through the process to get the coefficients, then get K, then calculate how much is going to be left later. So you'll find, and you'll see this on the practice test, I don't always tell you all the steps you need to do in between. That's part of what you're supposed to be learning. I'm going to ask you for something at the end. You're going to have to be smart enough to know, I'm going to go through these steps in order to get to the end. Okay, so you'll see that in the practice test. But so, you know, in this one, these are going to both be first order. When we come back, it's Wednesday, so yeah, when we come back Friday, you know, I'll show you how we're going to use this information and use the rate constant in order to be able to calculate how the concentration changes, you know, later on in time, and that we get the concentration. Yes, sir. Uh-huh.